Good day to you. The articulated skeleton is a common design feature of animals. By this, we simply mean that the skeleton consists of several rigid elements that are joined or articulated at joints. Movement comes from muscles rotating those elements around the joints. In insects, the skeletal elements are outside the body, forming an exoskeleton. In vertebrates, the skeletal elements are internal, of course the bones, which form an endoskeleton. Articulated skeletons are easy to analyze mechanically because simple principles of lever mechanics can be applied to their motion. Nevertheless, we are biologists first, and we should try to take a step back from our diagrams and equations and take a look at some real joints. And that's what we're going to do today, courtesy of Marshmills Farms and Manlius, who supplied us with several sets of articulated limbs from white-tailed deer. So here are two articulated limbs from a white-tailed deer. This is the hind limb, and this is the forelimb. Let's look at the hind limb first. Here's the joint. This is the equivalent to the knee joint here. This down here is the ankle joint, and this is where the femur joins to the hip. You can see the joint is very heavily encapsulated in fibrous connective tissue. That's to help hold it together. We'll look into that in a bit more detail a little bit later. But let's just look at how these joints rotate the bones around them. Let's look at the ankle joint first. Here's the ankle joint. You can see that it can rotate back and forth just like our own can. This is the ankle bone right here. And we'll get into some of the tendons that do that motion in a little bit. One of the things I want to point out is that there's only 1 degree of freedom of motion. That is, it can only move in this plane right there. If you try to twist the ankle this way, it's very, very rigid. It's very hard to make it move in this direction right over here. If we come up and look at the knee joint, on the other hand, we can see that it also can rotate about in this type of direction right here. And unlike the ankle joint, there's a bit of degree of freedom of rotation this way. So the knee joint can move mostly in this direction, but it has a limited ability to move in this direction right here. Okay, let's go to the forelimb now. Here's the forelimb. Here's the shoulder blade. Here's the shoulder joint. This is the equivalent of the elbow joint. These pins in here for a later demonstration. And again, you can see that this rotates about this way. There's an interesting catch mechanism right here, which we'll go into in a little bit more detail in a little bit. But again, this joint right here has very little ability to move in this direction right here. Most of its rotation is this direction. Unlike the hip joint, or unlike the knee joint in the hind limb, this is the shoulder joint here, and you can see that it has a tremendous amount of freedom of movement. That is, it can move in this direction, it can move quite a bit in this direction, it can rotate around, and so forth and so on. And this is important in helping the deer steer itself as it runs. Okay, so let's now take a closer look at some of these joints. We'll take a look at the ankle joint first. Okay, so let's take a closer look at the ankle joint. This is kind of a small one, and this one over here is better prepared because it makes the tendons stand out a little bit better. Let's take a look in some detail at the tendons. So here's the ankle joint. It rotates around. You can see the tendons in here showing up as glistening little cords of connective tissue. And what I'd like to do is focus on 2 tendons in particular. There's this tendon right here. This is our Achilles tendon, and this goes up to the equivalent of the calf muscle over here. And then there's this tendon right here, which extends up to the other large muscle of the lower limb. These, of course, have been removed because the hunter wants to meat. Now, we've spoken before about how tendons can come in either low gear or high gear varieties. Low gear, of course, is when the animal wants to accelerate, and high gear is what helps keep the animal going once it's at speed. And you can see that demonstrated quite nicely here. This, of course, is a type 1 lever. That is, the force is here, the fulcrum is at the ankle joint. And you can see here that these tendons attach at 2 different distances from the fulcrum. There's the Achilles tendon right there, and you can see that the distance is quite large. This is our low gear joint, and this is what the deer uses when it wants to accelerate away from a hunter or a predator that's trying to get it. And then there's this one right here, which is the high gear joint. And these are a little bit greasy, so we're going to grab our pliers and grab onto that a little bit better. And we'll just pull on this and watch what happens to the ankle joint. You can pull it up like so. Well, I need to get a better grip. Let's do that one more time. Let's get a better grip. And rotate that again. Now it's harder to do this. You can see that it's harder because I'm actually having a harder time pulling on this, but it takes more force to actually be able to move this joint around this fulcrum. And I have to pull quite hard on it. With the Achilles tendon, of course, I don't have to pull hard at all. Now there are other tendons here that are of interest. You can see this tendon right here. This tendon extends up to these muscles, and these pull the joint this way. One of the interesting things about this is you can see this little sleeve of connective tissue. This is a tunnel. This is what makes these joints behave as if they were jibs. That is, there's a fixed point here, and when you pull on this, even if you're pulling at an angle like so, nevertheless, the force exerted on the joint is always in the same direction because it's constrained by this right here. Okay, so here are two knee joints. This one is more intact. This is the femur. This is the tibia. You can see the kneecap right there. And you can see that this joint is encapsulated in muscle and connective tissue, quite heavy connective tissue right around here. And this, of course, helps hold the knee together. This knee joint over here, it was a bit damaged during the butchering of the deer, and you can see in some detail some more of the structures here. We spoke about the limited degree of rotation of the knee joint. It can move this way quite a bit, but it can't move this way quite a bit. The movement of the joint is constrained by these ridges and this groove right here, and we're going to open up this joint so you can get a better feel for what the other face of this looks like, and that helps constrain the rotation or the movement of the knee joint this way. Okay, so let's get busy. Let's start teasing some of this stuff away. There's the kneecap right there. Okay. Let's continue cutting. Now you can see the interface of the kneecap right there. That's the patella. These cartilages right here are what are damaged when you damage your knee. And let's take a better look at this right there. We still can't see quite how it's interacting with the tibia, but we can continue to cut away there. There's a big ligament right there. That's one of the cruciate ligaments that gets damaged if you play too much football the wrong way. Let's continue cutting. There's another one of the cruciate ligaments, right? Sorry, let's get right in there. Let's move this out of the way. You can see this ligament right there. That also helps hold the knee joint together. Let's cut that. There's some tissue right there that we need to cut away. You can now see the top of the tibia right now. This is quite slimy. There's another one of the cruciate ligaments right back there. Let's cut that. Now you can begin to see the top of the tibia right there. Continue cutting. Cutting through ligaments on the other side of the knee joint. Cut through some ligaments over here. Almost there. Here's one of the large lateral ligaments of the knee right here. You have to cut that. Cut up so we don't damage the knee. There we are. Finish cutting through these muscles. Now you can begin to see some of the detailed structure of the inside of this. There's more ligaments down there. But now you can see two large faces right there. Those are called condyles, and you can see how moist they are. Those are the joint ligaments, and they secrete a fluid known as synovial fluid. It helps lubricate the joint. And you can see that this round surface fits nicely into this cup of ligament right there. This is actually a ligament. These are some of the things that get ruptured in knee injuries. This is actually just a little patch of ligament that floats free in the joint. And if we take that away, then we can see the top of the tibia. Let's continue cutting. Okay. Let's take this away. Here, cut that ligaments right there. Now you can see, get a feel for what the structure of this joint is. Here is the top of the tibia right there. That is the cartilage on the end of the bone. This is what secretes synovial fluid. This sits on top of this like so. And then this condyle fits in there, and they rotate back and forth in a very, very smooth motion. Okay, compared to the relatively constrained knee joint, let's have a look at the shoulder joint, which has much greater freedom of motion. Now, this is the shoulder joint, this is the shoulder blade, this is the humerus, and if we open it up like this, you can see the cartilage. Now, this has been damaged during butchery. Normally, this is covered with connective tissue, as we saw in the knee joint, but it offers much greater rotation here. So let's just open up this joint like we did the other one. It's going to be much, much easier to do because there are fewer ligaments and tendons holding it in place. We start cutting away this connective tissue here, like so. Cut away some of this muscle. Joints are held together largely by muscle. That's why when you have a problem with the control of the muscle, you often end up with joint injuries. There's a ligament right here that we want to cut. Let's do that. There's another ligament right there that's been cut already for us, courtesy of the butcher. Here's more of this connective tissue right here that we want to get rid of. Open this up, and you can see that this is held together much more loosely than the knee joint was. Let's continue cutting down here, and now we can open this joint up. Right. So here is the top of the humerus right there, a nice ball surface over here. This is the base of the shoulder blade right here. You see it's a cup shaped, and if you look at how this rotates right there, you can get a feel for why it has so many degrees of freedom of rotation, of movement. That is, this thing can move in any direction. It's a lovely ball and socket joint right here. It's a fairly shallow ball and socket joint, but of course muscles and tendons and ligaments help do the job of holding it together for us. Let's start with the elbow joint, but on the deer. If we come down here to the deer, here's the elbow joint, here's the shoulder joint right there, here's the elbow joint. This bone here is equivalent to this bone here, and of course this is equivalent to my forelimb. Now the elbow joint of deer has kind of an interesting catch mechanism, and you can demonstrate it just by holding it up like so, and I'm going to very gently push on this bone right there. You can see it rotate around the bone, and when it achieves a critical point, it straightens out all on its own. And you can demonstrate the same thing by pushing back this way, and again, at a certain critical point, it closes all on its own. There's an interesting mechanism in the elbow joint. It's a catch mechanism, and you can demonstrate this by cleaning up this joint a little bit, and we're going to come over to this joint right there. There's the elbow joint, and we've taken away some of the muscle, and you can see some of the tendons as you rotate this. This tendon becomes slack, for example, and then it tightens up, and there's another tendon below this that you can't see as well, but nevertheless you can feel it's tensing up. That's the catch mechanism right there. And this catch mechanism depends upon some eccentric rotation of this, and we can actually demonstrate this quite nicely by using these pins as markers. And these two pins here are at either end of that catch tendon. This pin is down here at this joint right there, at this bone right there, and these two just give us an indication of what the rotation of that is. So what we're going to do is we're going to hold this up to the camera so we can see it properly, all right? And then we're just going to very gently rotate that around. We'll rotate it back. And what we can do now is we can use some image analysis to take a look at the distance of those pins as a function of the angle of rotation of the joint, and we can get a feel for just how much that tendon is being stretched at each angle of the joint, and we can get an insight into what the catch mechanism actually is.
The catch mechanism depends upon the stretching of this ligament, highlighted here, that joins the humerus to the ulna. As the ulna is rotated around the humerus, notice how the ligament stretches and then loosens. The ligament stretches until the joint passes a particular angle of flex, at which point the ligament springs back, pulling the bone along with it. The green and blue pins mark the distance between the ligament's points of attachment on each bone. For a catch mechanism, we might expect to see the distance between the pins first increase, then decrease as the joint rotates. In fact, this is what we actually see. There's obviously something more complicated going on. Okay, let's clean up this joint a little. Here's the humerus, and here's the ulna, and here's the rotation of the joint. We've peeled away these muscles to expose the condyles of the humerus. And this is the operation of the catch mechanism. Notice how this ligament, which stretches from here to here, rides over the smooth surface of the condyle as the joint rotates. As it does so, the ligament first stretches and then relaxes. The secret is in the surface of that condyle. Let's now cut that ligament away very gently and expose the smooth surface of the condyle. We can get a rough idea of the condyle surface's complex shape by passing a laser line over it. It's very complex. We can see, though, that the surface resolves into 3 high points, or nodes, spaced between 2 shallow grooves. And here's how the catch mechanism works. When the joint is flexed, the ligament is held in position by resting in this groove. As the joint is extended, the ligament rides up this ramp to the top of the node, and as it does so, it is stretched. Once it reaches the high point of the second node, it slides down to the second groove, drawing the ulna along forcibly with the energy stored when the ligament was stretched. The same thing happens in reverse when the joint is flexed.
So that's it. The physics of the thing is always interesting, but there's no substitute for getting our hands dirty and being biologists again. Until we meet again, this is Scott Turner wishing you a good day.